Hello and welcome. Today we will be looking at fluid flow past an object, specifically looking at boundary flow so that we can use that to understand fluid flow past an object or an automotive object and the features that we would typically see in the automotive environment which enable us to manage the fluid flow and the boundary flow past that object. So in this image we can see some wind tunnel testing which has been done on a Porsche 911. What I want to do in this class is help us to understand the shape of some of those streamlines going past that vehicle, why the flow is attached, why it's separating in certain places, and also the position of the wing at the back of the vehicle and what we would expect to happen there. Okay, in order for us to understand the image that we saw on the previous slide, we need to go back to some basics. We need to understand what boundary layer is all about. So we can have a look at boundary layer and how it develops on a flat plate. We can then move on and we can consider how that would what would occur on a curved surface, so that we can look at surfaces such as the automotive surfaces that you saw on the previous slide. We can then have a think about some of the tools which we can use to delay separation, and we'll talk about why delaying separation is advantageous, why we might want to do that, and then we'll move on and we'll have a look at some automotive examples and race car examples towards the end of this lecture. Okay, so before we cover the content in this lecture, I want to recap some of the concepts which are going to be discussed in this lecture, some basic concepts. So later on in this lecture, you'll hear me referring to these things, and I just want to clarify exactly what I mean by that. So to start with, viscosity and viscous forces. What do we mean by that? So what is the definition of viscosity? So viscosity is a fluid's ability to change shape. A very viscous fluid is very resistant to that change, and a less viscous fluid is less resistant to that change. And the viscous forces are those internal forces which are resisting that change. Streamlines and stagnation point. What do I mean by that? If we look at this image on the top right hand corner here of this Porsche, clearly we can see some streamlines there, or some smoke which has been introduced into the airflow, and those follow these streamlines. So what are streamlines? Those streamlines are paths which a massless particle would travel over a vehicle. So these represent the velocity vectors of the airflow around that vehicle. The airflow is clearly travelling in that direction. There's zero velocity across a streamline. So there's zero velocity perpendicular to these lines. The airflow is travelling from left to right there, following these positions. Turbulent and laminar flow. What do I mean by that? So a laminar flow is where we've got these parallel streamlines. The flow is organised, all of the particles are moving in the same direction, and we've got laminar flow represented by these parallel streamlines at the front of the vehicle here. In contrast to that, turbulent flow, we can see we're starting to see some turbulent flow at the back of the vehicle here, where there is, so at the front, the flow is organised, the flow is all parallel, and the velocity and the particles are all moving in an organised, structured, parallel way. At the back of the vehicle here, we can see flow moving in a disorganised way, represented or seen by these smoke particles which are merging. So clearly there is flow travelling vertically in a disorganised way at the back of the vehicle. So organised laminar flow, disorganised turbulent flow at the back of the vehicle. And we see that in this image here, So here we've got fluid flowing from left to right across this plate, and at the front of the plate we would have parallel streamlines. We've got organised flow, we've got laminar flow. So all of the flow is travelling from left to right in these sort of parallel lines in this organised fashion. Towards the back of the plate here, we've got turbulent flow. So our streamlines would be merging together, our flow would be mixing, and we'd see this sort of disorganised structure towards the back of the flow. Now we can actually use something called Reynolds number to define when we would see laminar flow and when we would see turbulent flow. There's the definition of Reynolds number. So Reynolds number, this dimensionless coefficient, the density of the fluid times by the velocity of the fluid times by some length. I'll discuss what that is in a minute. The characteristic length divided by the viscosity of the fluid. So this idea of understanding how viscous our fluid is represented by this term here, the viscosity. That's actually the dynamic viscosity of the fluid. So density, velocity, length, viscosity. Okay, so our fluid is travelling from left to right here, and in this case, this characteristic length will be the length along our plate. So as our flow increases along the length of our plate, our is clearly increasing. Therefore, Reynolds number is increasing. So towards the front of the plate, when our Reynolds number is quite low, we've got this laminar flow. As Reynolds number increases, because length is increasing, we start to see this turbulent flow. And this measure of Reynolds number tells us whether we're likely to see laminar flow or turbulent flow. So in this instance here, in this image here, our Reynolds number is below 1 × 10⁵. We've got this laminar flow, got this organised flow, we've got these parallel streamlines. Towards the back of the plate, as our Reynolds number increases, because length has increased, so Reynolds number is now up at 5 × 10⁵. We've got turbulent flow. So our Reynolds number will tell us whether we're likely to see laminar flow or turbulent flow. Bernoulli's equation, you'll hear me refer to Bernoulli's equation in this presentation. What do I mean by Bernoulli's equation? Well, Bernoulli's equation simply states that in one position, so position 1 in a fluid and position 2 in a fluid, the energy remains the same. We can't create or destroy energy. We just move it from one form to another form. So Bernoulli's equation basically says we've got this term here, which is associated with pressure. We've got this term here, which is associated with the kinetic energy. And we've got this term here, which is associated with the potential energy. So in all instances, in all places across our structure, the pressure, the kinetic energy and the potential energy remains the same. We can't create or destroy that energy. So if, as our fluid flows over our structure, we're likely to see an increase in velocity because of continuity of mass, or we're likely to see an increase in potential energy because our fluid has increased in height, we must see an associated drop in pressure. Okay, so in all instances, it remains the same. So if our height or our velocity increases, our pressure must decrease. So we can think about energy as our fluid flows across our object, and we can think about Bernoulli's equation. So how do we stop our boundary layer from separating from our object? You'll hear me refer to this idea of velocity in our boundary layer. And if our velocity reaches 0, we would see separation. So we need to try and increase the velocity in our boundary layer. One way of doing that is by encouraging the onset of turbulence. And you can see as we increase the turbulent flow, we've got this vertical motion. We increase the height of our boundary layer. And if we're increasing the turbulence earlier due to the mechanisms that I'll be talking about in this presentation, we're increasing the turbulence earlier, we're drawing down kinetic energy from outside of our boundary layer into our boundary layer. And if we're increasing the kinetic energy in our boundary layer by drawing down kinetic energy from outside of our boundary layer, we will encourage that velocity to remain positive, and therefore we would see attached flow later on because we've increased the kinetic energy in our boundary layer. So attached flow is when our boundary layer is still connected to our object. Separated flow would be when our boundary layer has detached from our object, is no longer connected to our object. If our boundary layer is still connected to our object, then if we see any reductions in pressure on the top of our object because of Bernoulli's equation, for example, if we see any reduction in pressure at the top of the object, obviously that would try and lift our object. So the definition of lift, we're trying to lift our object because we're seeing a reduction in pressure on top of the object. Conversely, if we see a reduction on pressure on the bottom of the object, clearly that would generate downforce. So generally in automotive terms, we would talk about downforce, so negative lift, and in aerospace terms, we would talk about lift, the idea of trying to increase the height of our object, trying to raise it up in the vertical direction. Drag, if our flow has separated, so it's detached from our object, what we tend to see is this low pressure turbulent region at the rear of our object. And if we've got a low pressure region attached to the rear of our object, clearly that's going to try and draw it in this direction. So if this object is traveling from right to left and we've got low pressure at the back of the object trying to resist that, then that is what is referred to as drag. So this idea of trying to resist motion, in this instance caused by this low pressure region, this wake at the back of the object. Okay, so those are the things, just to recap, that we'll be going through or you will be using in today's presentation. Okay, so we'll be thinking about viscosity, we'll be thinking about streamlines, or what I didn't mention, stagnation point. So when streamlines flow over our object, what the stagnation point is, it's the point where the streamlines would contact the front of the object. Clearly our fluid would be traveling from left to right, it would come in, it would impact our object, and at a certain position our velocity must be zero. Our pressure is at its greatest and our velocity must be zero because our fluids are coming in and striking our object. So our stagnation point is that point on the front of the object where our streamlines come in and contact the object. So we'll talk about streamlines, stagnation point, turbulent flow, laminar flow, Reynolds number, this idea of being able to quantify whether we're likely to see turbulent and laminar flow. We can also think about fluid flowing past our object in terms of the energies associated with that. We can then also think about trying to draw more energy into the boundary layer by introducing turbulence and growing the size of that boundary layer, and that will determine whether or not the flow is attached or separated, and ultimately how much lift and how much drag we are likely to generate from our object. On this slide we're looking at fluid flow over a flat plate. So the image on the right hand side, if we imagine some fluid flowing from the left hand side to the right hand side, it strikes the plate here. So upstream the fluid is travelling from left to right and is travelling with free stream velocity U infinity, so that's our fluid velocity when it's not being influenced by the plate. As soon as it strikes the plate, then we get the formation of our boundary layer. When we look at our boundary layer, that's what this line here is showing. So this is showing the edge of our boundary layer. So X is in the horizontal direction, Y is in the vertical direction. So we call delta the boundary layer thickness, and delta we can see clearly there is a function of X. And so as we move along the plate, the boundary layer grows. Initially, when our Reynolds number is quite small, so less than 1 × 10⁵, our boundary layer is laminar. At the back of the plate here, when our Reynolds number is very large, that's our Reynolds numbers 5 × 10⁵, roughly, our boundary layer is turbulent. And in between the two regions there, we have this transition region when our boundary layer is moving from our laminar area, laminar flow, to our turbulent flow. So what's happening within our boundary layer? As our fluid comes in from left to right, it impacts our plate. It's travelling at a certain free stream velocity, which we've called U infinity. However, as soon as it interacts with the plate, the fluid right next to the plate must be stationary. And the thickness of the boundary layer between the plate where the velocity is 0 and the free stream velocity outside of that boundary layer is dictated by the viscosity of that fluid. It's influenced due to the velocity gradient is influenced due to the viscous forces inside the fluid. So initially that boundary layer starts off quite small. The shearing action has not had a chance to develop. However, as the fluid travels along the plate, that shearing interaction grows, so that you can see that the boundary layer gets thicker as the fluid moves along the plate. Once we get above a certain Reynolds number, then that interaction is complicated by the fact that our fluid is no longer laminar. We're entering this transitional region, and then we move on actually and we get towards this turbulent region. So not only have we got the viscous nature of the fluids interacting in the boundary layer, but we also have the fact that our fluid is moving from a laminar flow to a transitional flow to a turbulent flow. So you can see the growth of the boundary layer as it moves along our flat plate is relatively simple. It's being influenced by the viscous forces inside the fluid. It is also being influenced by the fact that our fluid is going from a laminar flow to a transitional region to our turbulent flow. However, the pressure gradient across that plate is 0. We know from Bernoulli, as our fluid, as a fluid flows past a curved surface, the velocity changes and also the pressure changes. However, clearly we don't have that in this case. We've got a flat plate, so therefore the pressure is remaining constant. So therefore the boundary layer is being influenced simply by the viscous forces and the nature of flow within the boundary layer itself. So let's now look at a slightly more complicated case. Here we've got a similar scenario. Our fluid is travelling from left to right. However, instead of travelling over a flat surface, over a plate, which is what we saw on the previous slide, this time our fluid is flowing past this curved object. So our fluid is coming in, we've got our stagnation point where our fluid first interacts with our object, and then we start to see our boundary layer growing. In a very similar nature to what we saw on the previous slide, the fluid must be travelling at 0 velocity where it is interacting with the object, and then travelling at its free stream velocity outside of our boundary layer, and between the two there must be a transitional region where it's going from 0 velocity to free stream velocity. the thickness of that, like I say, is dictated by the viscosity within the fluid. However, to complicate things over our previous scenario, we now no longer have a constant pressure along the length of our object, because our object is now curved. So we know if we're increasing in potential energy as we go in this direction, the associated pressure must be decreasing. So as our fluid flows from left to right, we're seeing a favourable pressure gradient. And what I mean by that is the pressure gradient decreases in the direction of the fluid flow. So the fluid's trying to flow from left to right, the pressure is also decreasing from left to right, and that encourages the fluid flow in this direction. So our shearing action within the boundary layer is trying to slow our fluid down, and however the favourable pressure gradient is trying to increase the velocity of our fluid. So our fluid actually remains attached as we go along in this direction. However, once we pass this point, once we pass the shoulder of our airfoil, we have an issue. Our pressure gradient is now no longer favourable, it's adverse. And what do we mean by that? Well, instead of the pressure gradient being in the direction of the fluid flow, it actually goes in the other direction. So as our height decreases, we're going to start increasing in pressure. So our fluid is trying to flow from left to right. However, the pressure is now resisting that. Our pressure is actually going up as we go along the length of our object. So now not only is the viscous nature of the fluid trying to slow down the fluid within the boundary layer, the adverse pressure gradient is also trying to slow down the velocity of the fluid within the boundary layer. Now, why is that important? Well, when the velocity within that boundary layer reaches zero, that's when we start to see separation. That's when separation occurs. So these vectors here are representing the velocity of the fluid across our boundary layer, and you can see how they're decreasing due to this adverse pressure gradient until eventually it reaches zero, and then this shaded region here is representing our boundary layer, and you can see our boundary layer here has separated, and actually our velocity even reverses, goes in the opposite direction due to this adverse pressure gradient. So this region here is representative of our wake. Our wake is our low pressure region behind the airfoil, where our flow is actually reversed. Actually, we start to see this turbulence, this backflow in this wake, and we can see the boundary layer has actually separated from our object. Now, why is that important to us? Well, as soon as we start to see that separation point, we see the formation of this wake, we see reductions in lift, which can be generated by the airfoil because our fluid is no longer attached to the airfoil, and we also see increases in drag. The drag is connected to the size of this wake, which is behind our object. So if we have early separation, so the separation moves in this direction, the size of the wake is going to clearly increase, and therefore the amount of drag increases, and also the lift which our airfoil can generate is also reduced. So in order to reduce the amount of drag that our object sees, and to increase the amount of lift that our object can generate, or downforce if we're talking in automotive terms, we need to delay this separation point for as long as possible. And there's various ways that we can do that, and we'll look at that now. Okay, so we saw on the previous slide how the separation point occurs on an object when the velocity in the boundary layer reaches zero. So what we need to do is to try and delay that separation for as long as possible. to reduce the amount of drag that we would see within the on the object. An easy way to do that is to increase the amount of kinetic energy in the fluid in the boundary layer. So we're introducing kinetic energy, we're introducing velocity of fluid in the boundary layer, and therefore delaying the separation. So here's some examples of how we might go about doing that. So on the left, we can see up here on the upper image a slotted airfoil. So here we've got an airfoil, it's relatively high curvature, so without that slot the flow would separate due to that adverse pressure gradient, and that would result in increased drag and increased lift. So why do you see scenarios like this? Why do you see examples like this? Well, additional airflow is introduced from underneath the foil. So we're introducing kinetic energy on top of the wing here. So that introduction of kinetic energy will delay the separation point, and therefore we will see reduced drag, increased lift. Other examples that we might see are these vertex generators. So here's another aerospace example where we're using those that geometry there to introduce some turbulence, to introduce some kinetic energy within the boundary layer, and by introducing that kinetic energy, again we're reducing or we're delaying the separation on that object. Another example that you guys will be familiar with is shown in the centre of the screen here. Here we've got fluid flow past a sphere, past a smooth sphere. What do we see? We see that we saw what we saw earlier. Separation point is up here towards the top of the object, and we've got this relatively large wake, relatively large amount of drag being applied to this object. An easy way to delay that separation again is by introducing kinetic energy in the boundary layer, and therefore delaying that separation. So the example here is a golf ball that you guys are all familiar with. The flow again is introduced, the kinetic energy is introduced into the boundary layer, and therefore delaying the separation, and therefore reducing the size of the wake, and therefore the amount of drag which you would see on that object. And that's why golf balls have dimples in them. That's why you put dimples on golf balls so you can hit them further. So there's an example there. Another example that you might have come across is this idea of shark skin, this idea of taking lessons learned from nature and applying them to the engineering or product development world. If you look at a shark skin, if you zoom in, that's what these images are here are showing. We're zooming in on a shark skin. It's relatively rough. And why is the sharks, why have they evolved in that way? By having a relatively rough skin. Again, they're introducing kinetic energy in the boundary layer and delaying separation, and therefore reducing drag. There's been a trend over the last few years to take those and introduce them into swimming costumes. So here you can see the same idea by introducing small features on the surface of those objects, so introducing kinetic energy into the boundary layer, reducing the separation point, and therefore reducing the amount of drag which you would expect to see. So in all of these examples, clearly a reduction in drag separation point is advantageous in terms of performance. So now let's have a look at some automotive examples doing similar sorts of things where we're trying to delay the separation of the boundary layer from our object. So here's some examples of some vortex generators. So just like in the aerospace example that we saw on the previous screen, these pieces of geometry are introducing kinetic energy into the boundary layer, and therefore delaying when that occurs, when the separation occurs, and therefore the amount of drag which we would see on the back of those vehicles. The picture in the image, the image in the centre here showing this Porsche. A couple of things to talk about here. Firstly, we can see the shape of this has been extended. Again, thinking about the adverse pressure gradient. So by changing the shape of the back of that, you're reducing the adverse pressure gradient and therefore delaying separation, delaying the amount of turbulence that you would get off the back of this vehicle due to the shape of that vehicle. The second thing that we can see there is that when separation does occur, clearly this wing at the back here has had to be raised so that that wing is sat in laminar airflow, which is represented by this streamline here. If that wing was any lower, that would be sat in turbulent flow due to the fact of the separation of the back of that vehicle, and that wing therefore would not be able to generate as much downforce. The last example here on the right hand side, example of a slotted wing or representation of a slotted wing, similar to the aerospace example that we saw on the previous slide, where we obviously want relatively high curvature to generate a large amount of downforce on our vehicle, but due to that high curvature, what we expect to see is separation due to the adverse pressure gradient, and therefore a reduction in downforce and an associated increase in drag. However, an easy way to get around that would be to introduce these slots, which introduces airflow, new airflow into the boundary layer with increased kinetic energy, and therefore stopping that separation from happening. So those are some automotive examples where we have influenced the fluid flow within the boundary layer to delay the separation, to reduce drag, or to increase lift or downforce within the vehicle. The sources that I've used in this lecture are there. So if you want to do some more reading around the subject, and I recommend you do that, those sources are there for you to have a look at. As always, if you've got any questions regarding any of the information that we've covered today in terms of the fluid flow or the boundary layer formation around an object, please email me.